Welcome to Real Analysis P4, Logic and Quantifiers. Before we write proofs, we should decide what our sentences actually mean. Mathematics is strangely demanding about that. A proposition is a declarative sentence that has a definite truth value, true or false. For example, 2 plus 3 equals 5 is true, while 2 plus 3 equals 7 is false. Both are propositions. Truth and falsehood are properties of propositions. Being emotionally persuasive is, regrettably, not a third truth value. The expression x squared is at least 4 is not yet a proposition if x is unspecified. It is an open sentence, or predicate. Once we assign x a value, or bind x with a quantifier, the predicate becomes a proposition. From propositions P and Q, we build new propositions using logical connectives. The negation, not P, reverses the truth value. The conjunction, P and Q, is true only when both statements are true. The disjunction, P or Q, is true when at least one statement is true. Mathematical or is inclusive unless someone explicitly says otherwise. A truth table records every possible combination. It is not glamorous, but neither is debugging a proof built on the wrong meaning of or. The implication P implies Q means, if P is true, then Q must be true. An implication is false only when P is true and Q is false. That is the one case where the promised conclusion fails. When P is false, the implication is declared true. This is called vacuous truth. And yes, logic has found a respectable name for keeping a promise that was never activated. For every real x, if x squared equals -1, then x is greater than 10. This is true because no real x satisfies the hypothesis. The converse of P implies Q is Q implies P. It is a different statement and may have a different truth value. The contrapositive is not Q implies not P. Unlike the converse, it is logically equivalent to the original implication. For real x, x greater than 2 implies x squared greater than 4. Its converse is false because x could be -3. P if and only if Q means both P implies Q and Q implies P. The two propositions always have the same truth value. Accordingly, an if and only if proof has two directions. Writing obviously between them does not count as the missing direction. In P implies Q, P is sufficient for Q, while Q is necessary for P. Sufficient points forward from the hypothesis. Necessary points backward from the conclusion to what must have been present. The universal quantifier means for every. The existential quantifier means there exists at least one. The domain of quantification matters. Saying every x satisfies a property is incomplete unless we know where x is allowed to live. For every real x, x squared is non-negative. There exists a real x whose square is 2. But there does not exist a rational x whose square is 2. The formula stayed put. The domain changed the answer. To negate a quantified statement, switch every to there exists. Or switch there exists to every. And negate the predicate. Not every x satisfies P means there is some x that does not satisfy P. One counterexample destroys a universal claim. There does not exist an x satisfying P means every x fails to satisfy P. For example, negate, for every positive epsilon, the absolute value of x is less than epsilon. The negation is, there exists a positive epsilon such that the absolute value of x is at least epsilon. Notice that less than became at least. With multiple quantifiers, order matters. For every real x, there exists a real y greater than x. This is true. Choose y equal to x plus 1. Swap the quantifiers. There exists a real y greater than every real x. This is false because the real numbers have no largest element. In for every x there exists y. The choice of y may depend on x. In there exists y for every x. One fixed y must work for all x. Those are not stylistic variants. Swapping them can turn a theorem into ambitious fiction. To prove a universal statement, take an arbitrary element of the stated domain and prove the property without assuming anything special about it. To prove an existential statement, produce a witness and verify that it works. Arbitrary does not mean random, and chosen does not mean arbitrary. The first must represent every case. The second only needs to provide one successful case. Here is the working vocabulary. Connectives build propositions. Implications have direction. And quantifiers say how many elements must satisfy a predicate. Always track the domain. Negate both the quantifier and the predicate. And never rearrange quantifiers merely because the symbols look tidier. Next, we will use this language to review direct proof, contrapositive, contradiction, induction, existence, uniqueness, and counter-examples. Logic supplies the grammar. Proofs are where we find out whether we can actually use it.